Hey everyone, Mr. Johnston here. This is kind of a little interesting topic. It's something you've probably heard a little bit about, or maybe I've mentioned a little bit about because I found this is one of the coolest topics I learned in college. And so I actually just want to give a little kind of mini unit with a couple small kind of short lectures. Maybe we do a little bit of kind of the numeric stuff so you can kind of see some of the really neat, powerful things that this does. But I just want to talk a little bit about relativity. And relativity, kind of as the name implies, and it tells how things are relative to each other, and that relates really to lengths and events and time, which is kind of a weird topic in and of itself. And so there's two kinds of relativity. There's special relativity and there's general relativity. And so special relativity, this is actually the first one that Einstein came up with, and we've all known Albert Einstein. We got him right here. Arguably one of the most influential thinkers in history. He's the reason why GPS works, actually, because you have to incorporate special relativity into it. Otherwise, like, your GPS is gonna actually get very, very far off within about a day or so, and you'll be about 15 minutes or so in lag, which is kind of bizarre. So You've also heard like the equation equals mc squared, and that kind of relates mass and energy together. And we've talked in our kind of unit on gravity that that mass kind of warps this fabric of space-time. Well, energy also does the same thing because we have this. Oh, thanks, Java. Because we have E equals mc squared. This actually kind of relates energy and mass together. So they're kind of two sides of the same coin. So if you go, well, mass warps space time, this kind of fabric of reality that we are sitting in, so too does energy, which is very bizarre and hard to kind of wrap our heads around, I know. And so his theory on special relativity, it's called special relativity because it works in a very special case. Special relativity only actually works in the case of things moving at constant velocity. So it's a very special case because a lot of times things are accelerating or decelerating. So special relativity, again, really works. So we have special relativity. This works in the case of constant velocity. Um, and even more so, so really that means that acceleration is zero. But even more kind of exciting is it actually works in the case of high speeds, though. So constant velocity, but large velocity magnitude. And just for magnitude, I'm just going to put the absolute value bars because we kind of get that means magnitude now. General relativity. This one, as the name kind of implies, is literally more relative. It actually came out later. It's more general in scope, and it's really the theory that describes black holes, that curved space-time that I was talking about, and actually the evolution of the universe, which is kind of neat. It's an awesome story, but it's kind of beyond the scope of this textbook and kind of this class and everything. So we're just kind of gonna stick to it at that. So it's beyond our textbook. It's beyond really the scope of the class, but it's pretty freaking awesome. But it involves some really high-powered mathematics. Um, so more general and describes black holes, kind of curved space-time, and the evolution of the universe. So sounds like some pretty wicked cool sci-fi stuff, though, I gotta say. Now, this top picture that I put in here, We have the compact muon solenoid detector. It's a mouthful. At the LHC, Large Hadron Collider, it's the world's biggest particle accelerator, and it's where protons are accelerated to 99.99999% the speed of light. So they're wicked fast. Now, the speed of light is given the symbol c. It's so common. Um, we use this every once in a while, and the speed of light, aside from just being huge, it's actually 3.00 times 10 to the 8 meters per second. Or putting that in like normal notation, we have 3 and we have 8 sets of zeros. So 1, 2, 3, 4, 5, 6, 7, 8, and then there's a comma, and there's a comma. So 300 million meters per second. So it's very, very, very large, stupendously large in all honesty. So these particles get going 99.99999% that speed. So they're essentially going the speed of light, and things get weird when things start going really fast. And so, aside from kind of introducing just these two topics and comparing general and special relativity, I want to talk a little bit about reference frames. So, a reference frame, this is just kind of a new term, a new definition, really. So, a reference frame. And a reference frame is really, I guess, a coordinate system. So it's like I'm sitting here right now and I'm in my own reference frame. I'm just sitting here. You could be walking, you could be on a train, but essentially, a reference frame is just some coordinate system where, like, people, experimenters, can make position and time measurements. So, a coordinate system, oops, let's make this in black. Coordinate system where experimenters can make position and time measurements. Now, other things can be measured, but we're just going to stick to those two because it's kind of a special set of measurements. And this can be on moving objects. Okay, so couple things. Reference frames actually extend to infinity in all directions. So if I'm sitting here, there's like a z axis coming up out of my head, and maybe there's a y in front of me, and there's an x to the left, for instance, or to the right, actually, is what would be a better set. And those actually kind of go out towards infinity. The other thing that's really important is that experimenters are at rest. So I'm at rest right now. Experimenters are at rest in the frame. Now, here's one thing I have to mention though. If I'm sitting in my car and I'm going on the highway and I'm going 65 miles per hour, in my reference frame, as long as I'm not speeding up or slowing down, I would be at rest because I would be sitting still in my car. And I could argue pretty solidly that instead of me moving on the road, it's actually the road is moving beneath me. So either it's you're the reference frame of the ground and I'm moving 65 miles per hour north, or you're in the car with me and we're saying that we're sitting still and the road is moving 65 miles per hour south, which is a weird way to think about it, I know. So that's kind of the main things, and you can have as many people as you want in a reference frame. So aside from that, I have to introduce one kind of last term here, and it's an inertial reference frame. This is kind of an important one, actually, more so than just general reference frame, even though getting that to the kind of the basic idea is important. Inertial reference frame. Now, Newton's first law is the law of inertia. So maybe that kind of clicks a little bit, and you're like, well, what the heck? Like, if something has more mass, it's harder to push. So that things at rest kind of stay at rest, things in motion kind of stay in motion. That's the first law. How does that really kind of relate? So actually, an inertial reference frame is just a reference frame where actually all of Newton's laws are valid. That's it. A reference frame where I'm going to move this down there. A reference frame where all, let's underline that, Newton's laws are valid. So it works in all of them. Essentially, we're saying we're not accelerating, we're not doing anything weird like that. So it's kind of where it's there's an if there was a particle in this inertial reference frame, then we would say that there are no forces, things either remain at rest or they move in a straight line at constant speed. So that's really what this means. So things stay the way they are. That's kind of what I'll put underneath. Things stay the way they are. That's really what we mean by it. And maybe should we do a little sample here? Yeah, let's do it. Let's do a quick little sample. I think I have one down here. Yeah. Okay, so here's what I want to show though. This is kind of a great example of talking about reference frames. So we can have two different reference frames. And let's say here, this is kind of our standard reference frames, really. This is kind of the gold standard, maybe you'd say. So we got standard reference frames. Sorry, also, my handwriting is trash because we've been out of school for so long, I haven't had to write as much. So let's say that we have two different reference frames. We can have reference frame S and S with a little comma. So kind of just like P and P prime, as we called it during momentum. We'll call this S and S prime. So we can kind of view these two reference frames. We'll kind of say these two are always our standard, kind of our basic idea, basic package. We'll say that we can have that, well, reference frame S is stationary, and S prime would be moving over there to the right. And that's totally fine. It's moving to the right over at speed v. It's not speeding up. It's not slowing down. And that's it. Now, the one other important thing to note, actually, though, is that originally these were at the same position. So actually, S prime originated right here. So there was S prime, but since it's moving over here at some later time, there it is. So that's really kind of what this is showing, that originally at time 0, they were like stacked on top of each other. And then at some later time, they've kind of moved apart from each other. So we have these two reference frames. Or maybe you argue that, yo, I'm in this one. And if I'm in frame S prime, it seems like I'm actually standing still. So instead, I would say then that frame S started over here and frame S moved that way. And so later we have frame S. Later, at some time, it's kind of jammed along over here, and now there it is. So this is kind of our basic way of comparing reference frames. Now, they're moving at constant velocity, though, or depending on whose reference frame you're in, no velocity, but even 0 is a constant. So I know that's kind of weird. So with that kind of in mind, let's just look at a problem. So we have an airplane. It's flying at this speed with respect to the ground. So if you're standing on the ground, the plane zooms by you at 200 meters per second. Cool. Sound wave 1 approaches the plane from the front. Okay, so here's sound wave 1, and it's moving to the left, and the typical speed of sound at like normal atmospheric pressure and normal temperature, under weird conditions it changes, but the speed of sound is that. So that's it. Now, the speed and the sound wave 2 is catching up to the plane from behind. So here we have it here, and so the plane's moving to the right, this sound wave is moving to the right, and so it's trying to play catch up, essentially, is the whole idea. Both waves travel at 340 meters per second. That's the speed of sound, kind of typically at standard temperature and pressure. what is the speed of each wave relative to the plane? So really it's saying that the plane is the reference frame we want to use. It's not saying pretend you're on the ground, it's saying pretend you're chilling here on the plane. So you're here on the plane, and there's some mathy equations we can talk about, like Galilean transformations. I don't want to do that. Let's just use common sense here. So if I'm on the plane and the plane's moving 200 meters per second, but to me on the plane, I am sitting still, right? Our reference frame is stationary. That means that this 200 doesn't exist to me. But I gotta say though, this wave is definitely moving towards me faster than 340, right? Because if there was someone chilling down here on the ground, that, whoa, hey, this one's moving at 200 that way, this one's moving at 340 that way. So it's kind of like they're moving towards each other then, right? At 540 meters per second, right? It's kind of the idea that if you're driving on the road at 50 miles an hour and someone else is driving the opposite direction at 50 miles an hour, and if two cars were hit, it would be equivalent to a 100 mile per hour accident, right? Because you could see it as you sitting still and them hitting you at 100, or them sitting still and you hitting them at 100, or vice versa. So relative to the plane, we get that for wave one. Wave number one, and this is, I'm not going through kind of the fancy equations for it, but we just get that since they're moving towards each other, we get that we have to add those two velocities together. So we're actually going to get 540 meters per second, but since it's going to the left and our axes are positive y is this way and positive x is that way, this will be negative 540 meters per second, because if I'm sitting here, this wave is going to appear like it's going 540 meters per second that way to the left. So for wave two, well, this one has to play catch up now, right? So it's kind of like, I don't know, you're skateboarding down the road and maybe you're skateboarding at 10 miles an hour and someone passes you and their speedometer says they're going 30. Well, they're only going 20 miles per hour faster than you, right? So that's all it is. So if I'm already going 200 meters per second this way, but in my reference frame, I'm sitting still, instead of me moving to the right at 200 and the wave traveling at 340, because that's what this guy sees down here, right? Well, instead, it's just going to look like I'm sitting still and the speed of this wave is just dropped by 200, because if you're subtracting 200 off mine to put me at rest, you're subtracting 340 off this one to keep it in the same reference frame. So we get it that this one is positive 140 meters per second. And so it's all relative. It's kind of weird because this guy down here on the ground, he sees them both moving at 340, one's to the left, one's to the right. But to the guy on the plane, it doesn't seem to be that way. So that's kind of what we're talking about with reference frames. I hope that made sense, and we'll just leave it at that for today.